Hello students and welcome back. So today we're going to be exploring the hydrogen atom. In this video we'll be looking at it mathematically, so looking specifically at the wave functions and manipulating them. In the next video we'll be exploring them visually using a web app. So let's think back to our hydrogen atom model. So remember we have a proton and an electron that are separated by some distance. That distance can change. We can think about them being separated by a spring where they can stretch. And then we also have rotational motion. I know I've only drawn the blue arrow in one direction, but really we could also rotate in and out of the page as well. And so stretching is described by the radial wave functions, which are denoted with a capital R, and they depend on two quantum numbers, n and l. While rotation is described by our spherical harmonics, which were our wave function solutions to the rigid rotator. Remember these y functions, and they depend on quantum numbers l and m. So what ties them together is quantum number l. So there are three dimensions that can change. Remember, we're changing in spherical coordinates. This is r, theta, and phi. And because there are three dimensions which can change, that means there's three quantum numbers, n, l, and m. So when we write out our wave function, which again we're going back to psi for the hydrogen atom, it depends on three quantum numbers, n, l, and m. It changes with respect to three dimensions, r, theta, and phi, and it's written as radial function times spherical harmonic. So we have a function describing sort of the change in distance, the change in r, and then a function describing rotation, or the change in these angles. So remember that these y functions are what we already talked about. This is just our rigid rotator solution. So let's look a little more in depth at the radial wave function, or r. So it also has a normalization constant, much like what we've been seeing. So n depends on n and l. We're going to multiply that by r to the L power, where L again is one of our quantum numbers. Then we have an exponential term, which our exponential function is raised to the is raised to the minus r over na naught. And then we have a Laguerre polynomial, which is this end part here. So this is our polynomial for the hydrogen atom wave function, specifically for the radial component of this wave function. And so let's look a little bit at n. So our normalization constant, they seem to just keep getting a little bit more complex each time. So our normalization constant for our radial wave functions look like this. So it's negative quantity n minus l minus 1 factorial divided by 2n times n plus l factorial raised to the third, all square rooted, times the quantity 2 over na naught l plus 3/2 power, which is kind of crazy, right? This is getting, again, a little bit more complicated than our rigid rotator was. You don't have to have these memorized, obviously, as we've been doing so far. I will continue to give you equations, right, and expressions like this, but you should be able to use this expression. So a naught shows up a lot here, kind of like h shows up everywhere in quantum mechanics. All of a sudden with the hydrogen atom, we get this quantity a naught that starts showing up everywhere. And so what is a naught? A naught is often called the Bohr radius. It comes from the Bohr model, and it's epsilon 0, which is our permittivity of free space, or the dielectric constant of a vacuum, times Planck's constant squared, notice that this is h, not h bar here, divided by pi, the mass of an electron, times the electric charge squared. So this is the Bohr radius. It's just really a constant, right? We can look it up. It's a number. All right, so let's talk about these Laguerre polynomials and give a few examples. So L11 as a function of y is minus 1. The next one, L21, we see gets a little more complicated. It's negative 2 factorial 2 minus y. And they continue to get a little bit more complicated. Notice that there is a pattern. Whenever whenever n plus l is equal to 2l plus 1, you get sort of a nice number for your polynomial. When those two quantities aren't equal is when you get these kind of situations where you get a factorial times a polynomial. So there are some trends that go on there in the Laguerre polynomials. All right, so let's write out a wave function. Let's practice. So we're going to go for psi 210 which is the wave function when n is 2, L is 1, and m is 0. And we're going to talk a little bit more about what these wave functions, what these quantum numbers within this wave function represent in the next video where we look at these visually. And maybe you're hearkening back to Gen Chem and you're like, oh, I recognize N, L, and M. And maybe you're like, no, foreign language, it was a long time ago. Either way, it's fine. Again, in the next video, we're going to look at these visually and we'll go into more detail as to what each of these quantum numbers really means when we look at them visually. All right, so let's write out this wave function. So we want to write out psi 2, 1, 0, which is going to be the radial function for 2, 1 times the spherical harmonic of 1, 0. So let's start with our radial function. So r2, 1 is our normalization constant for 2, 1 times r raised to the 1 times the exponential function of minus r over 2a naught times our Laguerre polynomial for 2 plus 1, 2 times 1 plus 1, all as a function of 2r over 2a naught, which of course we can get rid of those 2's, which we'll get there. So let's start with our normalization constant. So if we're plugging in 2 for n and 1 for L, we can write out our normalization constant like this, and we can start to simplify. So this top part over here, we can see that we have 2 minus 1 factorial. What does that go to, ladies and gentlemen? Well, it goes to 0 factorial. And then at the bottom, we can see that we're going to get 4 times 3 factorial cubed. Remember, all of that is raised to the 1/2 and then negated. And then we have over here, our 2's cancel out. We're left with 1 over a naught in that second part. And then 1 plus 3/2 is going to give us to the 5/2. So we've got some things to deal with. Let's see if we can't simplify. 0 factorial, remember, is just defined as 1. And then we can get 4 times 3 factorial is 6, so 6 cubed. We're going to leave that as 6 cubed right now. We'll deal with it later. And so one way that we can deal with the 6 cubed is by saying we have all of this right here is square rooted, right? So we can take 4 square root is 2, so the 4 becomes 2. 6 cubed square root is really the same as saying 6 times the square root of 6. So we're going to go ahead and make those adjustments just to simplify it a little bit. And then we still have our 1 over a naught to the 5/2. Okay, so let's plug that into our radial wave function. And then we have the rest of our wave function to contend with. So r raised to the 1 is simply r. We have our exponential. Now we need our Laguerre polynomial. So just a reminder from the previous slide, the Laguerre polynomial for 3, 3 as a function of y is negative 3 factorial, and negative 3 factorial is just negative quantity 3 times 2 times 1, or negative 6. So we can just plug a negative 6 in. Well, that's not so bad. We can simplify a little bit because we have, note, a negative 12 over here. So that is just going to become 1 over 2 square root of 6 at the beginning. 1 over a naught to the 5/2 r. And then we have our exponential function. And ta-da! We have a radial wave function. So this is what our radial wave function looks like. It certainly doesn't quite look like a harmonic oscillator. However, it's sort of taking the place of a harmonic oscillator. So though it doesn't quite look like it, it is going to act a little bit like one. So it is a little bit mathematically different if you go back and look at your harmonic oscillators. They do look a little bit different, but we still have sort of a similar shape and purpose to this function. Okay, so now let's contend with our spherical harmonic, which is just from our rigid rotator. So if we think about y10, it's going to be some normalization constant times the Legendre polynomial times our exponential function is actually going to go to im phi, and m here is 0. So that's just going to go to 1. That's kind of nice. So what is the normalization constant for 1, 0? So we can write this out. We're going to get 2 plus 1 over 4 pi times 1 factorial over 1 factorial, all square rooted. So 3 over 4 pi. 1 factorial over 1 factorial is just 1, or 3 over 4 pi square root. Not so bad. So let's plug that in. So 3 over 4 pi square root. And now we need to know what our Legendre polynomial, these p function, we need to know what that is when L is 1 and m square root of, absolute value of m is 0. And so that, as a function of cosine, is simply cosine theta. So if we plug that in, we get our nice y function. And so to get psi 210, we simply need to multiply our radial wave function times our spherical harmonics. Let's go ahead and do that. All right, so when we multiply them together, we notice that we can pull all the constants out front, right? So this whole thing is the normalization constant, and it's really the product of the normalization constants from the two, right? So it's 1 over 2 square root of 6, 1 over a naught to the 5/2 comes from the radial wave function, 3 over 4 pi to the 1/2 comes from the spherical harmonic. So this is just the product of our two normalization constants. And then we're left with the radial function times the spherical harmonic function. All right, so I'm going to go ahead and break this into two videos. So the next video, we're going to apply psi 210 and try to calculate an average value.